So now it's possible to also have an observer who is moving, okay? When an observer is moving towards a source, okay, the idea here, so towards the source, right, the observer is going to encounter more waves per second. And what's going to result is a higher frequency. All right? Moving away from the source, the situation here is that the observer is going to encounter fewer waves per second, and a lower frequency or pitch will be observed. All right? The big question here, okay, is a moving source equivalent to a moving observer? Now, before I said that the effect on frequency was similar, but it is not the same. Okay, we got to be very, very careful about that. Velocity of each is with respect to the medium is not the same. Okay, so in other words, the moving source, okay, we have a stationary observer there typically, and so the velocity of the observer relative to the medium is not the same. But with the moving observer, pardon me, the wave speed relative to the medium of the observer, all right, is the same as that just in the medium. But with the moving observer, your wave speed effectively changes. Okay, and so that's a different effect. All right, it's not the same. So the equations that we have again, all right, for this one equation, but with the plus or minus makes it two equations. So again, the important thing to remember is that a moving observer, you have a different wave speed that you're observing. That's the main idea, because you have the motion relative to the medium. All right, so here, U naught is the speed of the observer relative to the medium. Again, a little mnemonic to help remember which one is which. All right, the little practice problem that is there, we're going to calculate the shifted frequency, right, for that situation. This is security alarm going off, and you're walking as you drive towards the car. Okay. What does the frequency seem? What is the frequency you perceive if you are moving towards it at this speed? Speed of sound is this much, and the original frequency is this much. Okay, and then when you solve for this, we're adding, right? Since we're going to be moving towards the source. This is the shifted frequency. All right? So the last piece of this here is going to be the Doppler effect as it deals with electromagnetic radiation. Okay? So we're not studying relativity, and when we're dealing with the Doppler effect and electromagnetic radiation, you need relativity to properly derive the formula. Okay? So instead we just have an approximation. So what ends up happening, all right, is when the source and the observer have relative movement towards each other, we end up being blue shifted. So blue shifted, we can think of that as the frequency increasing or the wavelength decreasing. Okay, but this is any time the relative movement between the source and the observer are towards each other. Okay, so here we don't care which one's moving. Redshift is when the source and observer are moving away from each other. So for the reasons that I showed before, we see that wavelength getting longer, okay, when there's relative movement away from each other for the source and observer, and we see that wavelength getting shorter when there's relative movement for the source and observer moving towards each other, okay? So the equation that we end up with here, all right, is this one. That the shift in frequency, that is the change in frequency, is equal to the ratio of the relative speed between the observer and the source divided by the speed of light times the original frequency. Okay. Here, of course, the speed of light, 300 million meters per second. All right. This works when V is much less than C. Yes, that is a double less than sign we use to relate when something's much less than something else. Delta F is just equal to F prime minus F, okay? And V is the relative speed of the observer and the source. Okay? V as being the relative speed here, all right, is going to be positive if it's towards, negative if away. So positive if towards, and that affects your F prime, negative if away. Okay? And so the example there, let's see here, V, the speed of the star relative to the Earth, it's moving away, right? So since it's moving away, it's going to be negative here, right? And it's going to be 3 times 10 to the negative 5, or excuse me, 3 times 10 to the 5, not negative 5. Meters per second. C is here. Okay, and let's see here, original frequency 6 times 10 to the 14 hertz. So we solve for the change in frequency, the frequency shift, right? And it's going to be negative. All right, so the shift is going to be negative 1 times 10 to the negative 11, it's going to be positive 11 hertz. All right, so it's a small shift, but it's a noticeable one nonetheless, okay? I mean, this is how, this blue shift, red shift idea is how we often determine whether things are moving towards or away from us. Actually, it's the main way we determine it. So the big idea, all right, here is that to be able to determine if it's blue shifted or red shifted. And so if you solve for the new frequency, you would see that this is blue shifted. Excuse me, it is red shifted. Take that back. Red shifted as it is moving away from us. Okay? If we're moving towards us, it would be blue shifted. There we go. All right? All right, that's it for the videos for today.